Zombie insects sounds like fiction until you realize it's an observed pattern in nature. In some infections, the host doesn't just get sick, it ends up in a location and posture that maximizes fungal reproduction. The impossible part is obvious: fungi don't have brains. So what exactly is being controlled? The mind, the muscles, or the environment? Let's investigate the mechanism that makes this look intentional. Zombie fungus is not a single species or a single trick. Multiple fungal lineages infect insects, and only some show behavior shaping outcomes. That matters because it hints at evolution solving the same problem in different ways. If similar behaviors appear across unrelated pathogens, the control might be less mystical and more biological logic. The first step is separating myth from what's consistently documented. The invasion begins with contact. Spores attach to the insect's cuticle like tiny anchors. Entry doesn't require dramatic wounds, it's a combination of adhesion, pressure, and enzymes that unlock the barrier. Crucially, early infection can look normal from the outside. That delay is strategic. A host that still moves normally is a host that carries the pathogen farther. Control starts only after the fungus has a foothold. Inside the insect, the fungus isn't a single lump, it becomes a distributed network across tissues. That changes the control question. Behavior can shift if energy supply, muscle performance, or signaling chemistry is pushed off balance. You don't need to invade the brain first if you can reshape how the body functions. Think of it as rerouting an organism's internal priorities. The host is alive, but its physiology is being rewritten. Insects fight back with immune defenses, so successful fungi often dampen or evade those responses. This is where the infection becomes asymmetric. The host loses options while the fungus gains momentum. Without immunosuppression, many zombie stories would end before they start. It also explains why behavioral changes are typically late stage. The pathogen invests in manipulation only after survival is secured. First, win the internal war, then, shape the final outcome. Before the famous, final pose, many cases show early drift, wandering, trail abandonment, or unusual isolation. This is not a dramatic mind control moment, it's a subtle breakdown of normal routines. For social insects, separation is critical. It reduces help from nestmates and increases the chance the host dies away from the colony. The behavior looks like a mistake, yet it benefits the fungus. That's our first clue: outcomes matter more than intent. One recurring pattern is upward movement. Hosts climb to elevated surfaces before death. Height improves dispersal. Spores released from above travel farther and land on more potential hosts. The strange part is how repeatable it is across different systems. If this were random sickness, we'd expect random death locations. Instead, we often see location selection that matches a dispersal advantage. Now the plot tightens. The fungus doesn't just need the host to die. It needs the body to become a stable growth chamber. Humidity, temperature stability, shade, and airflow can determine whether spores mature or fail. That means the destination isn't emotional or cognitive, it's environmental. The insect is being delivered to a microclimate the fungus can exploit. The behavior looks like navigation, but the target is physics. The iconic moment is the death grip, a locked bite onto a leaf vein or plant structure. This anchors the cadaver so it won't fall into conditions where fungal growth fails. A random dying insect would collapse anywhere. This one ends in a precise mechanical clamp. That clamp isn't poetic, it's functional engineering by evolution. The next question is brutal. Does the fungus command the brain, or simply lock the muscles? In several studied systems, fungal activity is concentrated in muscles that execute the final grip. That supports a disturbing possibility. The fungus may not need to pilot thoughts at all. If it can force hypercontraction in specific muscles, it can produce a behavior that looks intentional. The host's nervous system might remain partially functional while the output is mechanically hijacked. Control, in this model, is biomechanics plus chemistry. Notice the structure of the strategy. First, move the host to the right environment. Second, lock the body into the right posture. Those are two separate problems, navigation and anchoring, and fungi appear to solve both. That's why the story feels programmed. Even if each step is triggered by different physiological disruptions, the combined result looks like a plan. The investigation becomes: which triggers map to which step? After death, behavior stops mattering, reproduction takes over. The fungus builds structures designed to release spores efficiently into air currents. This is the payoff stage. The insect becomes a platform, not a victim. The earlier manipulation only makes sense in light of this final step. If the cadaver is in the wrong place, the spore factory fails. So how does a fungus coordinate changes without nerves? One model focuses on secreted molecules, effectors that alter host metabolism, stress responses, and excitability. Instead of one mind control switch, it may be dozens of small biochemical nudges. Stack enough nudges and you get a predictable behavior outcome. That's less cinematic, but far more plausible. Not every fungus forces a death pose. Some systems appear to bias behavior through compounds that change activity patterns and transmission chances. That's not muscle locking, it's behavioral probability shifting. Different fungi, different tactics, same objective: spread. This diversity is a key clue that zombie is a category, not a single mechanism. Our investigation has to track the strategy, not the stereotype. Colonies are hostile territory for pathogens. Ants can detect sickness cues, isolate individuals, and remove threats before spores spread. That pressure can select for stealth, keep the host normal long enough to escape the nest. The manipulation may start as an adaptation to social defenses, not a standalone trick. In other words, the colony shapes the fungus as much as the fungus shapes the host. Many of these fungi are picky: specific hosts, specific habitats, specific outcomes. That specificity suggests the mechanism is tuned to particular physiology and ecology. A universal zombie formula would infect everything the same way, but nature doesn't look like that. The lock and key pattern implies coevolution across long timescales, which makes every new documented case a data point in an ongoing arms race. Entomopathogenic fungi are already used as biological pest controls in some contexts. Understanding manipulation could improve targeting and reduce chemical pesticide reliance, but it also raises ecological caution. Introducing or amplifying pathogens can ripple through ecosystems. Natural doesn't automatically mean harmless at scale. Any application must be evidence-led, tightly tested, and regulated. The biggest unresolved question is hierarchy: brain, hormones, muscles, or a sequence of all three. We have strong hints for muscle-level locking in some systems, and chemical biasing in others. But capturing the exact moment control changes hands is technically hard in real time. That's why the story keeps evolving with every better microscope and every new dataset. The mystery isn't hidden, it's still being measured. The zombie mechanism isn't a supernatural takeover, it's a biological chain of cause and effect. Move the host, lock the body, build the spore launcher, and the genes spread. But the exact control map, what triggers what, still isn't fully solved across all systems. If it sounds impossible, we investigate it. Subscribe, and stay with the case.